Hey guys, so this is the lecture, it's not really a lecture video, the review video for exam 3. Sorry it's so late, I've actually already recorded it, but I messed up some of the recording, so we're doing it again. Okay, so I'm just going to run through what I had already written verbally. It's probably going to be pretty fast, but you guys can always pause this. Anyway, also I wanted to say please take your time on the exam. I think a lot of you did worse, or if you did worse on the previous exam than you expected, I have a strong belief that's because you went too quickly. I can see how long you guys are spending on this, so please take your time, write out your solutions. Don't just try to get through it as quickly as possible. All right, there will probably not be a makeup exam on this one, so don't put your faith in that. All right, so the first thing I want you guys to know is what a local minimum, a local maximum, and an inflection point look like. You guys should probably already know this, but it's just like a quick reference. I want you guys to know L'Hopital's rule, which is something we did pretty recently. It's for taking limits. So, for example, if we're taking the limit as x approaches 8 of x squared minus 14x plus 48 over sine of pi x, if we plug this directly in, we get 0 over 0. And so we've learned that previously we would have used like an algebraic tool, but actually there's no good algebraic tool when we're dealing with sine, so this is a perfect reason to use L'Hopital's rule. And in L'Hopital's rule, you just take the derivative of the numerator over the derivative of the denominator and then evaluate the limit as normal. So this will be the limit as x approaches 8 of the derivative of x squared minus 14x plus 48 is 2x minus 14. And the derivative of sine times pi x is cosine of pi x times the derivative of pi x, which is just pi, so that's where we get this pi out front. And when we plug in x equals 8, we get 16 minus 14, which is 2, and pi times the cosine of 8 pi, which is pi, because the cosine of 8 pi is the same as the cosine of 2 pi using the unit circle, or you could just plug it into your calculator. And this is 1. So we get pi times 1, which is pi. Okay. Something that happened before spring break was related rates. I believe it was section 3.11. And I did post the lecture notes, the like written lecture notes like these on YO courses for the sections before spring break. So if you need a refresher, which you might because it was a long time ago, that's where you'll find that information. This is like a pretty easy example, so if you don't feel good with this, I would definitely say to go review the lecture notes. Okay, so for this example, we're going to say that the edges of a cube increase at a rate of 2 inches per second. And then the question is asking us, at what rate is the volume of the cube increasing when the sides are 10 inches long? So we have a rate, the edges of the cube, 2 inches per second, and we want to know a different rate, the volume of the cube, at a certain side length. So, here I mean edges and sides to be the same thing. Anyway, okay, so first of all, because edge length is changing and it's the variable we'll be dealing with, we're just going to call it x to keep things simple. And we know that x is a function of time, right? Because our edges are increasing at a given second, or our edges are increasing as time goes on. So we know that the rate of change of our edge length with respect to time, which is what dx dt means, is 2 inches per second. That was just given to us in the problem statement. And we know we want to deal with the volume, so we need to relate our edge length to volume. And we have an equation for that. Hopefully you guys are familiar with the fact that the volume of a rectangular prism is 2 pi r. That's not even related. Okay. Is base times height times length or width. In this case, because it's a cube, all of those are the same thing, so it's just x cubed. It is important to note that x is technically a function of time, as we talked about it up here. So when we take the derivative of the volume to find the rate of change of the volume, we're going to have to do implicit differentiation. Sort of. It's more just the chain rule. But we did something similar to this when we did implicit differentiation. So we take the derivative of v with respect to t, and we get 3x squared. And then because x is a function of t, we need to multiply it by x prime of t. So the derivative of x with respect to t. That can just be rewritten as 3x squared times dx dt. And this question is asking us, what is that? So this is the general rate of change of the volume at any given, sorry, not at any given time, at any given length, edge length. But we are trying to find it specifically for the edge length of 10. So we're going to evaluate dv dt at x equals 10, which gives us 3 times 10 squared times 2, because dx dt is 2 all the time. And we're thinking about the edge length being 10. Note that 10 represents inches, and this is a really, sorry, I made a mistake in my answer earlier. Anyway, good catch. This should be in inches squared, right? Because 10 is in inches, and then we're squaring it, so it's inches squared. And then 2 is our dx dt, and that's in inches per second. So we get 600 inches cubed per second, which should make sense because we're in cubic units for volume, and then we're doing it as a rate of time, so per second. All right. I also want you guys to remember that the derivative of the natural log of x is 1 over x, and to remember to use the chain rule if x is anything that's not just x. So if we were to take the derivative with respect to x of the natural log of x squared, we do get 1 over x squared because it's just 1 over the inside. But then we need to remember to multiply by the derivative of the inside, which is 2x. And if we simplify this, we'll get 2 over x. So that's just a reminder of the natural log and the chain rule. This is where I ended in the last video, so we'll pick up here. I do want you guys to remember what a linear approximation looks like. So for example, if we're looking at a function that has a local minimum and we're trying to approximate what that function value is at that local minimum, we have the linear approximation, which we called L of x. And at a given point alpha, so at x equals alpha, the linear approximation at alpha is equal to f of alpha plus f prime of alpha times x minus alpha. And we talked about this and where it comes from in class. So if you need a review, please go back to that section. But right now, for our purposes, we'll just look at the basics. So this is the slope of our approximation. And that's the slope of L of x at alpha, this f prime of alpha. And so if I were to ask you guys what the slope looks like at different points, it's just the tangent line, because we know f prime is a tangent line, or the slope of a tangent line. So we could draw in little tangent lines to represent our f prime at those given points. And so if we were to ask, like, what's the slope of the linear approximation to the left of our value c? We can see that these slopes are negative. Or what's the slope of our linear approximation to the right? We know that the slopes are positive. If you note, both of them, as they approach c, are flattening out to approach 0, because that's what a linear or a local minimum does. A local minimum and a local maximum have tangent slopes of 0, which means the derivative is equal to 0 there. And if the derivative is equal to 0 there, then the slope of our linear approximation is equal to 0 there. So that's just kind of a reminder on how those are related. Again, I know this is quick, but it is very helpful for your exam, so I don't feel too bad. Okay. Let's see here. I did want to chat briefly about linear approximations. So remember, this is the linear approximation of f of x at alpha. So we have f of alpha is approximately equal to L of alpha, which is equal to f of alpha plus f prime of alpha times x minus alpha. But f of alpha does not equal this usually. So usually there's a difference, and if we were to calculate the error, for example, percent error, which is something we haven't fully talked about, but I wanted to introduce you guys before the exam. If it's on the exam, they will for sure give you an equation, but I want to talk about it just in case. So if you're familiar, if you've ever taken a lab class, you've probably calculated percent error before. If not, don't worry, it's just an equation. So it's 100 because to change a decimal to a percentage, you have to multiply by 100. And then it's the absolute value of the approximation minus the exact value over the exact value. And in the case of a linear approximation, that's just 100 times our approximation is L of alpha. So whatever you would get by calculating this guy. And our exact value is f of alpha, which you would have to find using a calculator most of the time. But because you guys are allowed to have calculators on this exam, and you also have access to Symbol Lab and such, it shouldn't be too bad. So then you would divide it by your actual value, f of alpha. It should always be a positive number because that's what these are. The absolute value is just the positive value. So yeah, that's an introduction to that. Again, it's new, but it's just an application of the linear approximations, not actually a calculus topic. Okay, what else? I want you guys to know min and max problems. So, for example, what are the two positive real numbers whose sum is 15 and which have the smallest possible product? So remember, a sum is things being added together, a product is things being multiplied together. So to solve this problem, we need to introduce two variables. Our two positive real numbers, we're just going to let them be x and y. And we know that x plus y is equal to 15 because up here we have that the sum is 15. Okay, so that's what we know. We want to minimize the product, x times y. And we're just going to call this P for product so that we have an equation. And right now, P is a function of x and y. And in order to minimize, we know that we need to take the derivative because that's how max and min problems work. But in order to take the derivative, we need to have just one variable. So the good news is we have this equation up here, the x plus y, equaling 15. So we can solve for one of our variables and plug it into our second equation so that we have just one variable. So x plus y equaling 15 gives us y is equal to 15 minus x. So P, which is equal to x times y, is equal to x times 15 minus x, which can be rewritten as 15x minus x squared. And we want to minimize this. So to minimize it, we first need to take the derivative with respect to our variable, which we have chosen to be x. So if I take the derivative, I'm going to get 15 minus 2x. And we want to solve for x when our derivative is equal to 0. And this will give us x equals 7.5. And because x plus y is equal to 15, we have 7.5 plus y is equal to 15, which gives us y is equal to 7.5. So if I'm looking for my two positive real numbers that give me this result, it's 7.5 and 7.5. So that's a different problem than we've seen before, but it's the same exact application of a max and min problem. So I want you guys to be prepared for using the tools that you have on things that you haven't seen before. Just a couple more things. Let's talk about what absolute maxima look like. So, or absolute extrema, sorry, not just absolute maxima. So, as an example, if I have f of x, ooh, weird. If I have f of x looking like this on some interval alpha to beta, I could ask you guys, does f of x have an absolute let's start with minimum. Min on alpha to beta inclusive. And the answer is yes. And it can be found right here approximately. That's just our minimum value on this interval, which we can clearly see is here. And then another question is, does it have an absolute maximum on this interval? And the answer here is no, because it would be up here at this point, but if you were to zoom in on this point, because this function is not defined right here, it actually goes on and gets infinitely close to that point. And so there's no actual real maxima. The maxima would be that point, but it doesn't exist. So the answer there is no. Two more things. I want you guys to remember that f of x is increasing when f prime of x is greater than 0. F of x is decreasing when f prime of x is less than 0. And f of x is neither increasing nor decreasing for f prime of x equaling 0. We talked about that, I believe, at the beginning of chapter 4. And finally, I want you guys to remember just what a derivative itself means. So we know that it's a rate of change. And we also know it's the slope of the tangent. Line. We also know that that means it's the instantaneous slope. So I guess the rate of change of f of x, if we're talking about f prime of x, it's the slope of the tangent line to f of x, and it's the instantaneous slope of f of x. So for example, if I say that f prime of 2 is equal to 4, this means the instantaneous slope of f of x at x equals 2 is 4. So if I were to ask you guys which of the following could be f of x as described here, let's say we had A, B. Honestly, guys, I'm impressed with this example, so give me that. And C. And they looked like this. Oh, wow. And 1, 2, 3, 4. This. And this. So just to rule things out, we know if we look on this guy, we're talking about the instantaneous slope of our function at x equals 2 being 4. So if we look at x equals 2, our function has a negative slope right here. So we know that it couldn't be 4 because 4 is a positive number. So we know that this guy is not it. All right, if we look at this guy, here at 2, our line is flat, and even though our f of x is equal to 4 here, the slope of f of x is 0 right here. And so 0 is not 4, so we know that this can't be it. So by deductive logic, we know that it has to be this guy, but let's just check to make sure because we are good math students and we know to take our time. And so if we look here, we have 2, and here it's a positive slope, and it looks fairly steep, so it being 4 is reasonable, and we can be pretty confident that we have the right answer. Okay, so that's my review for you guys. The exam technically opens at 12:01 tomorrow, so like in less than 2 hours, but don't start it then. Take your time. Take the time you need to study. I highly recommend watching this entire video. Well, I guess if you're hearing this, then you've already watched it. That was dumb of me to say. Anyway, have your notes next to you. Have a calculator out. And good luck. Bye, guys.